I just sent out an email to everybody basically saying that the second Mobius assignment will be delayed till next week. It was scheduled for this week. I forgot about reading week when I was scheduling these, and so it really would basically be exactly the same material as the last one, which really is kind of pointless. And so we are going to delay it a week. So it'll be next week. Okay, so we left off basically, we had just finished the previous lecture. I think there was like the summary slide left. I'm not going to go back over that. You can take a look at the summary slide. It doesn't make a lot of sense to summarize a lecture that we haven't done in a week and a half. So we had talked about stereochemistry. We had talked about, I'm going to turn my video on. Talked about stereochemistry. We had talked about, assigning RNS. And so today we're going to finish off this discussion of stereochemistry before slipping into starting to talk about alkene chemistry. And then we're going to start talking about mechanism. So this is kind of like our last sort of purely preparative material before we get into, new organic mechanisms, which I think would be new to most of you. Okay. Need to minimize that. So today we're going to discuss Fischer projections. Now, I would not teach Fischer projections if I possibly could get away with it. They are required on MCATs. MCATs love them for whatever reason. I'm going to rage about these for the next 20 minutes or so. We are not going to assign RNS from Fischer projections because screw Fischer projections. There's practice in a textbook, but I am never going to assign a question like that on an exam or an assignment because I despise them with every fiber of my being. We are going to identify diastereomers and meso compounds, and we're going to understand how they differ in physical properties. And then we're going to talk about how one goes about obtaining pure enantiomers, and then how to figure out if you've got two molecules that they're enantiomers of each other or diastereomers of each other, and what all these words actually mean. We are going to skip the sections which are all about Fischer projections. So, what is a Fischer projection? It's an archaic way of showing three-dimensional shape back from before we knew that carbons were tetrahedral and before we knew what atoms were and electrons and protons and all that. So, I have no idea why they survived this long. So we're used to looking at tetrahedra like that. One way you can look at the tetrahedron is if you view it from the bottom here. If you look down the bottom, midway between the carbon 3, carbon 4 bond, or the atom 3, whatever, the 3-4 bond. If you look from that viewpoint, what you'll see is that, I have to make sure I get this right. Okay, we're looking straight on. The 3 is in my left hand, the 4 is in my right hand. They're both coming out towards me. I'm looking midway down, midway down this bond. The 1 will be vertically above me, 2 will be vertically below me, and they'll both be pointing away. This is a weird way to draw a tetrahedron because none of the bonds are in the plane. It's perfectly valid. It's still a tetrahedron. It's weird. This we can then represent as a Fischer projection where we draw all those lines flat. Now, it doesn't mean that those 4 bonds are in a plane. It means that the top one and the bottom one are pointing away from me, and the ones on the side are pointing towards me. And that is the Fischer projection. So I'm a huge fan of Emil Fischer. I'm really glad he's dead, actually, because if he was alive with modern chemistry techniques, every single chemist in the world would probably be out of a job. He founded sugar chemistry, amino acid chemistry, nucleic acid chemistry. He did a lot of the first organic reactions on things. He discovered a lot of mechanism, and he did all that where the only way you could analyze what he had was, mixing two things together and seeing if they shared a melting point. It's absolutely ridiculous. It's insane. It's a really I guess it's not really a. I talk about this actually about a class in my fourth year carbohydrate course because it's incredible what he could do with what he had. But so discover the structure of sugars. Yeah, he is definitely a man. Well, he is a man, but very impressive man. And I'm pressing buttons and nothing's happened. So he was the first one to basically discover a practical use for stereochemistry. It had been noted that there was stereochemistry, but no one understood what that meant. He was the one who understood that stereochemistry related to sugar structure, and that stereochemistry meant something physically rather than just being a weird thing that changes with light polarization. And he sort of said, okay, this actually has a physical representation in space. It's got to do with the three-dimensional arrangement of atoms. And he was the first one to propose that carbon was tetrahedral as part of this thing. So he was the first one to make peptides, showing that you can make peptides from amino acids. You can make these things that are really involved in life from things that don't have anything to do with life. I'm trying to not. I've got my normal clicky things aren't here, and because I'm on campus and none of my stuff works, so I'm just randomly pressing buttons. So he made the first nucleic acid. So again, he was able to make RNA and DNA from non-living stuff, which was important. And he's good at wearing glasses. I'm not as good at wearing glasses, but I also don't have as good facial hair. So I at one point I did actually have a minor shrine to him in my office, because even atheists need to believe in something. It wasn't quite as fancy as that. And again, sorry, my clicking's supposed to be faster. It's just really slow today. So Fischer projections are one massive mistake. They should be banned. They should be burnt. They should be destroyed. And they're horrible. So, what can you do with a Fischer projection? There's only one rotation you're allowed to do. You're allowed to rotate them by 180 degrees. That is allowed. You cannot rotate them by 90 degrees. You cannot flip them. You cannot do anything else you would normally do with a three-dimensional shape. The only rotation that's allowed is a 180-degree rotation. Rotation by 90 is not allowed. It gives you a different molecule. The way you draw them is normally you put the most oxidized carbon at the top. This is a convention from Fischer's work where he stuck the aldehyde or sugars at the top. And everyone after there has done it as well. So if you have an alcohol, you would stick the most oxidized carbon at the top. And so you have a choice of sticking this guy at the bottom or the top, or the left or the right, you stick him at the top. So to make a mirror image of a Fischer projection is pretty easy. You just switch the left and right ones for the other left and right ones. Left becomes right, right becomes left. That's kind of how mirrors work. So they're really easy to draw mirror images of Fischer projections. That's great. And you get the enantiomer when you do that, assuming that's not a meso compound, and assuming it has asymmetric carbons. So assuming it has an enantiomer, I guess, is what I'm saying. So we've already been talking about this, but you can test for chirality with Fischer projections. So if the mirror image cannot be made to look the same as the original with 180-degree rotation, it's chiral, because it's the only thing you're allowed to do. And if you can't do that, if that doesn't work, then you're kind of out of options. And molecules who have an internal mirror plane or whose mirror image is superimposable on themselves are not chiral, because they look the same as the original. So if I'm being really, I am going to do one single example of a Fischer projection. It is the only one I am going to do. And if in 3 years you're writing an MCAT, you can look back at these lectures, because they'll probably still be posted on YouTube. And you can go, I don't remember Fischer projections. Worth like 30% of your MCAT to draw something stupid. So R2 bromo 1-butanol. So the first thing we should do is draw out R2 bromo 1-butanol. Not a bad idea to draw it out. There's an OH. It's a butanol. There are 4 carbons. We'll count the carbons to make sure there are 4. Because counting to 4 is hard. It is 2-bromo. There's a bromine. Now I basically need to figure out if I should have that bromine coming in or out of the plane. If I'm just drawing a normal, non-Fischer projection, just a normal one. So we look at that. Let's just, we can assign priority around this guy, around this carbon. This is going to be our stereo center. See, I still say chiral center. I know it's wrong, but I can't help myself. The bromine is number 1. It's the heaviest thing attached to it. The next thing the lightest thing this thing is attached to is a hydrogen. Notice I'm not drawing in wedges at this point. I'm just keeping track of what's there. I've got a carbon and a carbon. They're both carbons, but this carbon is attached to an oxygen, whereas this carbon is attached to a carbon. So this is heavier. So this is number 2, that's number 3, and the hydrogen is number 4. I want R right now. These things, if I just look at the order of the 1, 2, and 3, I'm going counterclockwise if I go from 1, 2 to 3. So it looks like S. But it's only S if the hydrogen's pointing back and away from me. It's R if the hydrogen's pointing out towards me. So I'm going to quickly cheat and just draw in the right wedges, and it's R. Okay, so that's R. Now, I want to draw a Fischer projection of this. So what the Fischer projection says is I draw a straight line. At the top there, I've got a CH2OH because I put my most oxidized carbon at the top. That's the most oxidized carbon. The only carbon I'm going to be interested in my Fischer projection, of course, is the chiral center. So I can get away with writing CH2, CH3 down here. And now remembering that for a Fischer projection, the top and the bottom carbons on your vertical cross are pointing out and away from you. What that tells me is my eyeball has got to be staring at this carbon directly like that. With 2 on top, it's going to be back and away from me. 3 on the bottom, it's going to be down and away from me. Hydrogen is going to be in my left hand. Bromine is going to be in my right hand. And so that is the Fischer projection of R2-bromo-1-butanol. There is no way that you can assign R and S directly from the Fischer projection. You can't say, oh, it's always clockwise when you have this thing there. No, it kind of is chaotic. You actually need to take the Fischer projection. You need to convert it into a nice wedge drawing. You then need to rotate it and orient it so the fourth thing is pointing back and away from you and assign R and S. You cannot do it directly from a Fischer projection. So we can have another question, similar molecule, very similar molecule, and we can ask, why do I despise them so much? This obviously gives you three-dimensional information looking at it. It's kind of drawing things in three-dimensional space. It requires the same amount of lines, basically, as drawing a Fischer projection, except it's always true. So what I think is the Fischer projection doesn't give you any information that the sawhorse, like this line drawing zigzag structure does. So why would you ever do it? Because it's just more confusing. So how do I know what was on the left and on the right? So what I'm doing here is I know that this is my top group, is the most oxidized carbon. That's this side of the molecule. So that means this guy's my bottom group. That's this side of the molecule. Now I need to orient myself such that that is my top and bottom. So I kind of need to, with the way I've drawn it there, I'm going to need to sort of tilt my head like that. And if I do that, the CH2OH is above my head. The CH2 is below me, right? And they're both going back and away from me because I'm looking straight onto that carbon. And one of those is above and back, and one of those is below and back. And the hydrogen and bromine are both coming out into my hands because that's how the tetrahedron works. They're coming out towards me. And in my left hand, above the plane of this thing, is the hydrogen. That's my left hand. My right hand, I've got the bromine down underneath my desk. And so when I write myself, the left hand is holding a hydrogen, the right hand is holding the bromine. And that's how I know. Yeah. Yes, you want the carbon chain to be the vertical line. These ones are all Fischer projections with one carbon. That's really interesting. But normally they're sugars. They've got 5 carbons that are chiral. Everything has got lines, and so every chiral center is chiral. It's very silly. It's a deeply silly projection. So if we're looking at these, and we're saying, what is the relationship That is CH2OH. There's a CH2 and an OH. That is CH2CH3 because there's a CH2 and a CH3. That's how I got them, Nulia. Okay. So it's asking what is the relationship between these molecules down here? So I think we've mentioned this term, but we haven't yet mentioned. I just want to bring a term in here, and that's diastereomer. And so we've talked about enantiomers. Enantiomers are non-superimposable mirror images. Diastereomers are non-superimposable non-mirror images. So we're going to come back to what I mean by that because I just realized there's only one chiral center in this molecule, so we don't need to worry about diastereomers. So with only one stereocenter in a molecule, there's only one possible type of arrangement. Yeah, if you're looking at the bottom, wouldn't BR be in the left hand? No, BR is in your right because BR is going back into the plane away from you. Now, if you flip your head the other way and you have the CH2OH on the bottom, then the BR would be in your left hand. The hydrogen is in your left hand because your face is, here's your head, here's your body, your legs and your arms. You're a cyclops. If you can't see that, please build a model kit. I'm going to say this, and I know that 70% of you are going to ignore it and say, no, it's fine, I've got this. And I don't know why I bother saying this every year, but I try because I'm hoping that one year, like one magical year, people are going to listen to me because they're going to want marks. Build, like, for doing these kind of stereochemistry questions, for comparing enantiomers and diastereomers, get your model kits out. Like, you're a class, like theoretically there's 340 students registered in this class or something like that. There's 170 of you live right now. I would say that of the 170 of you here right now, maybe one or two of you are able to flip these things in your mind. I have trouble doing this, and I've been doing it for 20 years. I still have issues doing it, and I've been doing it day in, day out for 20 years. This is the first time you're encountering it. It is freaking hard. It is hard. It is hard. It is hard. If you are a sculptor who is used to flipping stuff around in 3 dimensions all the time, great. Or if you're some sort of space pilot, but you're like, second year students at University of Windsor, I doubt you're space pilots. So the rest of us, we see the world upright because we mostly stand upright, and things, you don't rotate the environment, you rotate yourself. And stuff doesn't rotate on you randomly in all sorts of different directions because all bonds are rotating. It's just really foreign. Really recommend building a model kit, playing with the model kit, mapping it onto the page, because going from the page to the model kit, rotating the model kit, going back to the page is something you can do. Going from the page, rotating your brain back onto the page is where you're going to make mistakes. You're going to make so many mistakes. So please, I cannot recommend more strongly to get out a model kit and do this. Well, I recommend you buy one. If you didn't like, you can buy one on Amazon. Still, they're available. There's tons of them. They come in all sorts of different price ranges. They vary. You can get anything from $10 to, you could spend $500 on a model kit if you want, but you can probably get something for $10. If you rotate 180 degrees, so Bennett asked, I think the misconception is how can it be rotated 180 degrees? Yeah, you can rotate this 180 degrees around the axis, but then the CH2OH is on the bottom, and the CH2, CH3 is on the top. And then, yeah, of course you switch them. That's allowed. But now the CH2OH is on the bottom. So if we're looking at these, we have got one asymmetric center. And so there's only two possibilities. Well, there's only one way you can rotate this 180 degrees. Because you rotate 180 degrees clockwise or 180 degrees counterclockwise, it's the same thing. There is no other way to rotate it. Like you as a cyclops can look at it that way, or you as a cyclops can look at it this way. You can't flip it because then these guys are coming out towards you, and that's not a Fisher projection. You're not allowed looking at it from this angle. This is banned. This is forbidden. You can't do this because the top and bottom have to be pointing back and away from you, and in this case, top and bottom will be pointing towards you. Yeah, it's R, but it's R because I'm looking at it that way. I'm looking at that. I can't tell from the Fisher projection. You cannot tell from the Fisher projection. It is not possible to assign RNS from a Fisher projection. I don't want to spend any more time on Fisher projections than I have to. Yeah, sure. Of course, you can turn your mic on, Bennett.
Okay, hi, can you hear me?
Yep.
Okay, so what I'm thinking more is you keep the CH2OH where it is, and you keep the CH2CH3 where it is, and you keep that vertical and you rotate the H and Br around that way. And that's why I think people are confused which is left and right.
Yeah, but you're thinking that it's that the CH2OH, CH2, CH3 is a straight line. It's not a straight line.
Yeah.
It
Okay.
does this. It goes away from you. So if you rotate around that, now it's coming towards you, and now it's not a Fisher projection.
Oh, okay. Okay.
It's not a vertical line. It's not a vertical straight line. We draw it as a vertical straight line, but it is not a vertical straight line. It is saying that the bottom one's going away from you, the top one's going away from you. You cannot rotate like that. The only rotation you can do is that.
Okay.
You can't rotate like that because now that's not a Fisher projection. Now it's pointing towards you. It's now incorrect. It needs to point away from you.
Okay, thank you.
And it's just because that is the rule of the Fisher projection, and it's because it makes no freaking sense. And this is why I hate it so much. Okay, so let's get back to so I did promise about 20 minutes of hate, and I'm at 22 minutes of hate right now. So I'll move back to these asymmetric carbons down here. Again, the only thing we're allowed to do to compare two projections is flip vertically. And so it's saying, okay, what is the relationship of B, C, and D to A? There's only two possibilities because there's only one asymmetric carbon. They are either enantiomers of each other or they are the same compound. Those are the only two possibilities, assuming that all the connectivity is the same, and it is. Everything's attached to the same four things. Okay, well, A and B, that's a 180-degree rotation, right? We take this, we flip it up, we take that, we flip it down, the bromine goes to the left, the hydrogen goes to the right. Left and right, bromine goes to the right, hydrogen goes to the left. As I said, I have trouble with left and right. So, A equals B. They are the same molecule. Now, it's not clear whether the good news is what we can see here is B and A. I thought they were really going to screw us and move things around, but they didn't. They kept the horizontal stuff horizontal and the vertical stuff vertical, so it's all good. If we compare A and D, these are clearly enantiomers of each other. They're mirror images, right? You draw a mirror, hydrogen's going towards the mirror, hydrogen's going towards the mirror, bromine's going away, bromine's going away. They're mirror images of each other. The methyl groups are there. These guys are there. They're non-superimposable because I can't superimpose them. That's right. Because I need to remember, the only thing I'm allowed to do is the 180-degree rotation. So A and D are enantiomers. They are non-superimposable mirror images. Similarly, C and B are clearly enantiomers. And since B and A are the same molecule, C is an enantiomer, are enantiomers. And A and B are same. That actually shows up pretty well in the blue. So this is how we can sort of figure out, is A chiral? Yeah, A has an asymmetric carbon. A has an enantiomer. If you have an enantiomer, you're chiral. So, You cannot assign. Now they've tried to do it here. It makes me really squeamish, and it looks kind of confusing. And then you have to rotate it and put it into a normal phrase. This is the only way to do it. You have to take your Fischer projection. You got to put into a zigzag or a normal tetrahedron shape, and then assign RNS that way. So for this course, you need to know that Fischer projections exist. They are stupid. That is my official statement on them. I'm actually famous on chemistry Twitter for hating Fischer projections. And the reason is I'm a sugar chemist, and normally these only get used for sugars, but they really haven't been used for sugars for 100 years. But everyone thinks sugar chemists use them, but we don't because they're stupid. And we shouldn't teach them anymore. So, okay. Diastereomers are everything that are every stereoisomer that are not enantiomers. So we talked about this, we talked about cis and trans, and we talked about cis and trans within respect to rings. I'm really sorry that the examples, I have to really update these and get rid of all the effing Fischer projections. But compounds with two or more chirality centers can have isomers that are not mirror images. So what we have here, just briefly, and it's got Fischer projections, but that's not the important part, is we can have a molecule here, which are mirror images of each other. We've got two asymmetric centers. They are both mirror images of each other. We have a mirror image. It is an enantiomer. We have a molecule here, two asymmetric centers. It is an enantiomer of each other. But we can have these two molecules, which are not the same molecule. They each have two chiral centers. This chiral center is a mirror image of itself. This chiral center is not. So the molecule as a whole is not a mirror image of the molecule. But it's not the same molecule. And this is a diastereomer. Another way to think about it is a diastereomer is a compound with two or more chiral centers. So one way to think about it is, this is a good working definition. I've never seen it written this way, but it's absolutely true. Enantiomer, all chiral center flipped. So what I mean by that is all S become R, plus vice versa. So if you have 20 chiral centers and all your S's become all R's and all your R's become all S's, you've got enantiomers. The only difference between those two molecules is how they, rotate plane polarized light and how they interact with enzymes in your body. One probably kills you, one cures cancer. There's a very fine line between curing cancer and killing you, though. Diastereomers molecule has two or more chiral centers, stereocenters. See, I wrote chiral centers up there. I'm going to go back and change that. One or more are flipped. But not all. So if you have 20 chiral centers and 19 of them are flipped, you're a diastereomer. You're not a mirror image. If you got 20 chiral centers and 20 are flipped, you're enantiomers. If you've got 20 chiral centers and 2 are flipped, you're diastereomers. If you've got 20 chiral centers and 0 are flipped, you're the same molecule. So enantiomers are all the chiral centers have changed, in which case you have a mirror image. Diastereomers are some of the chiral centers have changed, in which case you do not have a mirror image and it's not superimposable. And the same compound is none of the chiral centers have changed, which makes sense when you think it's the same compound. Those are the three possible situations for molecules that have stereocenters in them, along with being a meso compound where it's the same compound, even though all the chiral centers have flipped. And it's because they map onto each other. And I think we showed an example of that earlier. So you got this handy little flowchart. Those of you who like flowcharts and who doesn't like a flowchart. So isomers, same molecular formula, right? That's what that means. We've got constitutional isomers, structural isomers. That's when you got the same molecular formula, but stuff isn't attached the same way. You know, one molecule has an ethyl group and a methyl group. The other one has a propyl group. Two different things, same molecular formula. Those are very different compounds, very different properties. Stereoisomers, similar compounds, everything's connected in the same way to all the same atoms, but they differ in how they're connected in space. So you've got enantiomers, where all the chiral centers are flipped. And then you've got diastereomers, where some of the chiral centers are flipped. And then you've got two different forms of that. You've got cis-trans double bond compounds. So if you think of the double bond, they're stereoisomers, clearly, because everything's attached to the same thing. They're not enantiomers because they're not mirror images of each other, so they must be diastereomers. But there's no asymmetric carbons. So there's kind of sort of geometric isomers, and they're a subform of diastereomers. And then you have all the other diastereomers where we're talking about normal chiral centers, or normal asymmetric carbons, where some but not all of the stereocenters have flipped. No, there will never be a question on my assignments about drawing Fischer projections. There won't be a question on a final about drawing Fischer projections. There will be no further mention of Fischer projections once we're done this lecture. They will be as if they never happened. So a molecule with n asymmetric carbons can have up to 2 to the n stereoisomers. It may have less because of meso compounds. So we had 2-bromo-3-chlorobutane a few slides back. And so there's 2 chiral centers. 2 to the 2 is 4. There's 4 possibilities. Because you can have 2R3R, 2S3S, 2R3S, or 2S3R. Right? Every center can be either R or S, and it can be R, and every other center can be an R or S. 2 asymmetric carbons isn't many. Once you start getting up to 20, you got 2 to the 20. That's a very big number. That's a lot of different stereoisomers that can exist. So this is, again, okay, Fischer projections are a little handy for doing this because it's easy to see the mirror. But that gets in the way of my rant, and so I don't like this argument. But between you, me, and anyone who watches this lecture later, they can be a little bit handy for just keeping track of internal mirror planes. But that doesn't justify their existence. So you can have less than 2 to the n. So we have 2 chiral centers on this molecule, but you only have 3 compounds because one pair of the enantiomers, the 2s3r and the 2r3s, are the same molecule. And again, what we note there is you're flipping the stereocenter. R is going to S, S is going to R. They are different stereocenters, but the thing is carbon 2 and carbon 3 are the same freaking carbon because of symmetry in the molecule. And so in this case, you got 2 stereocenters. You can have 4 stereoisomers, but you only end up having 3 because 2 of them are degenerate. They're the same thing. So a meso compound is an achiral compound that has stereocenters. Usually asymmetric carbons. And so that's how you can end up with less than 2 to the n stereoisomers. Okay. Draw each compound in its most symmetric conformation. I think that's kind of up to you how you define most symmetric. Star, the asterisk is kind of like the universal symbol for a stereocenter. And draw any in a mirror planes and decide is it chiral. Let's start with whatever you want. You need a picture. All these get posted. I don't know how far back, Nulia. I wasn't paying any attention to the chat window for a bit. Okay. All these get posted online, so you can always go and look at these things later. You don't need to run. You want to do the second? Okay, let's do the second one. Good idea, Quinn. I like that too. Okay. So only one of these carbons is looking suspicious to me, right? Like this carbon is not particularly suspicious as a potential stereocenter. It clearly has two hydrogens attached. This is the one that looks a little suspicious. So before we go off half-cocked just drawing random shit, let's think about, is it a stereocenter? So again, what do we need for a stereocenter? We need it to be attached to 4 different things. So I guess the question I've got is this carbon attached to 4 different things? Okay, Quinn thinks yes. So, okay, we're getting a bunch of yes votes coming in. We have a dissenter. Chiral centers are not a thing. When I say chiral center, I mean stereocenter. A molecule is chiral, a carbon is a stereocenter. Okay, we're getting some no's, we're getting some yeses. Let's look at it. Okay, so I'm going to just draw the carbon up here, and we have 4 positions. Okay, so let's look. This is obviously a carbon attached to an oxygen. It's got an oxygen down here. That is obviously, there are no other oxygens. That is obviously unique. Here, it's a carbon attached to a carbon. That's also a carbon attached to a carbon. That's also a carbon attached to a carbon. It's got a whole bunch of carbons attached. Not clearly unique, not clearly different. But pretty quickly, I hope by inspection, you're looking, well, this is obviously clearly different because carbon, 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 oxygen is different than the other ones because they don't have oxygens in their ring. You'll eventually hit something different. Now this is where this gets tricky. This is attached to a carbon. It's attached to a carbon. Both are CH2s. This is a CH2 going all up from this guy. If I could switch colors faster, I would like to do that. That's also a CH2. Then we're kind of swapping places, and we're walking down the chain. This guy's attached to a CH2. This guy's attached to a CH2. Then the one that would, again, going along this way, this carbon is attached to a CH2, and then to this carbon. Whereas when we were going the other way, it was attached to a CH2, then this carbon. This carbon and this carbon are actually identical because you go all the way around the loop and you get back to where you started. You go all the way around the loop and you get back to where you started, and they're completely the same. Those are the same thing. Now, it's a little confusing because it's a ring, but if I had drawn 2 propyl groups on there, like 2 CH2, CH2, CH3 chains, you would have gotten those are the same thing. Yeah, there's this fancy stereocenter that's drawn in there. Like we got wedges. Wedges are confusing, but and like there's a lot of carbons, and that carbon's making 4 bonds to other carbons, and I'm trying to delete, and no, I don't want to do that. I want to delete. So it's kind of throwing you off. But this molecule is achiral. And one way we can look at it is, does it have a mirror plane? And yeah, it does. So I'm going to draw the cyclohexane flat. It's not flat. It's, of course, a chair. But let's pretend it's flat for the sake of purposes, and that's okay. and that cyclopentane ring is going to be perpendicular. There's a mirror plane in the plane that's formed kind of by, because it's going to bisect, that mirror plane is going to bisect the cyclohexane ring. So all these atoms will lie in the plane. These two will be above, those two will be below, and they're directly mirrored on each other. This molecule has an internal mirror plane. And it's because this is the same as that. So those of you who said no, that this molecule is not attached to 4 different things, you're right. 2 of those things are the same. So let's say chiral. We take a look at this guy over here. It's not easy to tell if it's chiral or achiral right now. But, we can kind of cheat. We can draw it as a hexagon. We don't need to worry about these chair conformations. That's what we've got. I draw its mirror image. If I was a better drawer, it would be a better mirror image. But you can sort of get the idea, like everything is equidistant from the mirror. And when I draw them that way, it becomes pretty clear that if I just do a little bit of a rotation by 60 degrees, this carbon is going to be down here, and it's going to be like that one. So both my bromines will then be up, and this is going to be a superimposable mirror image of each of itself. This molecule is achiral. This is a meso compound, though. This is not a meso compound because that is not a stereocenter. This one is, because those are all stereocenters. It's just that they map onto each other. And so it's superimposable on its mirror image. I'll leave A as an exercise. So we talk about diastereomers. Enantiomers have identical physical properties except rotation of plane polarized light and messing up biology. Diastereomers have different physical properties. And it's because stuff is arranged differently in space relative to other stuff. And so you're going to have dipole moments are going to be different. Stereochs are going to be different. Stuff bumping into stuff is going to be different. The stuff is just different. So you see this with cis-trans isomers. And we see it with, normal sugars. Like, all your sugars are the same. Glucose is really sweet. Galactose is much less sweet. They differ only by the stereocenter at the 4th carbon. All the other ones are identical. But they have very different melting points. And they behave very differently. The chemistry is really, really different on these two, which is very, very frustrating. So diastereomers, because they have different physical properties, they are completely different molecules. Like, they just happen to share connectivity, but they don't behave like they do. They are different. So you can separate them using normal methods like distillation, crystallization, or chromatography, because they behave differently with matter. Now, enantiomers, the whole problem is they don't behave differently with matter. So how do you separate them? Well, there's basically the only way you can separate enantiomers is to make them not be enantiomers. So you need to trick them into not being enantiomers. Great, but they are enantiomers. So one really common way of doing this is, and actually there are kind of examples up here, you grab a pure sample from nature. So one of my tartaric acid, this guy right here, Louis Pasteur was the first one who separated these, and that's how we got the whole idea of enantiomers, because he was able to isolate both enantiomers pure and show that they change plane polarized light. And it's kind of cool how he did it, because he took a mixture and he collected crystals. And you can imagine that, and you got two separate different crystals. So if you looked at an individual crystal, one crystal would move plane polarized light one way, another crystal will move it the other way. And that's because as the crystal is growing, it's only adding to one enantiomer of the molecule. It's not adding the other one because the crystal wants to be very regular, right? So it's always adding the same enantiomer to it. So when you pull out two crystals from the same mixture, one is one pure enantiomer, the other one's another pure enantiomer, and you get the crystals big enough, you can actually do something with that and use it to separate. So he noticed that. In nature, we can actually get pure one enantiomer of tartaric acid, and we actually get it from wine, which is great. So you can take this and you can take, so let's say we have one pure tartaric acid enantiomer. Got this one. Awesome. Now I take an amine, and let's say I have a chiral center on my amine. I don't know. Those of you with a interest in pharmaceutical agents of dubious legality, I recognize this guy. This is actually something that gets done to prepare starting materials for making meth. So you can take tartaric acid and you can take a mixture of these two amines. Now they're a mixture, they're a 50-50 mixture because you made them 50-50. Now what happens, of course, is you get an acid-base reaction. That's not how that exists when you mix those two together. That goes negative. That goes positive. So you get salts. And now these two are talking together. Or it can talk to this one, this enantiomer. But this has chiral centers. So now you're making a salt. You're taking one enantiomer with set chiral centers, or another enantiomer with set chiral centers. And those salts are diastereomeric to each other. Because in the salts, this chiral center is flipped, but these ones are the same. So now you have two different compounds, you have two different salts, and they behave different physically, and you can separate them out through selective crystallization. This is called chemical resolution. And the idea is that we can collect one enantiomer and not the other. The other thing we can do, so we can make salts. So here what you can do is you can take a chiral acid and a racemic alcohol. It's chiral, but it's racemic. You got to make sure both. You can connect the two together and not make a salt. You can make an actual covalent bond. Now this has got a stereocenter. This has got a stereocenter. And if this is set and this is variable, kind of like what we have here, using RR tartrate in both cases, but you have either R or S-T-butyl. These are not the same molecules anymore. They're not enantiomers to each other. They're diastereomers, and now you can separate them using chemistry. Yeah, these are pretty typical MCAT kind of questions. Modern techniques, we'd often do this using chromatographic resolution. So we would have something packed into, what time is it? Yeah, we're good. I'll finish this lecture. We'll have something packed into a column, be little beads, and on the surface of that beads is one enantiomer or something. And so if I pass a racemate over it, that racemate is going to interact with that enantiomer, but the two enantiomers that are in the racemate, which again, a racemate is a one-to-one mixture of two enantiomers, will interact differently with the pure stuff on the column. One's going to interact stronger than the other one. And so what you'll do is you'll slowly separate them. One's going to be more tightly bound, one's going to be more loosely bound. So by the time you get to the bottom of the column, one enantiomer comes off first because one is more tightly bound and comes off second. And so we can separate the two enantiomers this way. And this is called chromatographic resolution because originally it was all about color. It's got nothing to do with color. It's got to do with binding stuff to stuff. I'm not going to ask you very many questions. No, you know what? On a normal exam, in a normal year, I might ask you some questions about, hey, how would you name me 2 ways to separate enantiomers? Give me 2 possible ways of doing this. I'm not going to do it now because it's straight out of your notes, and I can't evaluate you on questions that are straight out of your notes because there's no point. So I'm not going to ask you any questions on separating enantiomers on the exam. So Fischer projections are a thing that exists. Diastereomers are stereoisomers that are not mirror images of each other. So again, diastereomers are stereoisomers where you flip some, but not all, of the stereocenters. Compound with n asymmetric carbons can have up to 2 to the n stereoisomers. Meso compounds are achiral even though they have asymmetric carbons or stereocenters in them. And are achiral because they are superimposable on their mirror image. They're the same molecule. The mirror image is the same molecule as the original one, even though they have stereocenters. Diastereomers can be separated based on physical properties because they are differentially arranged in space. And enantiomers, you need to end up making some sort of diastereomeric interaction. You need to trick them into thinking that they're diastereomers to separate them, because otherwise they interact with everything in absolutely identical ways because they are literally mirror images of each other. Okay. There's some more practice problems on these. I'm probably going to post the next assignment of my practice assignments up. The next Mobius will be in 2 weeks. If you haven't looked already, you can. I accidentally had the settings set so you couldn't look at the answers even after the period was over. That's been corrected. You can look at your answers. You look at your answers and you feel a question was there's one particular question which for whatever reason Mobius is misgrading. If that's a question, you look at them and your answer and the correct answer look identical. Email me. We're going to give you the extra marks because I don't know what's wrong with this stupid computer program. Something's wrong. And so how many? I don't know. I've got 6 or 7. I'm going to start just posting them all. I just need to go through them and I need to make sure that I don't have mistakes in my answer keys, because I do have mistakes in my answer keys and I can never remember what the mistakes are in my answer keys. Do you need to know the 2n rule? Well, you don't need to memorize anything, right? Probably. I don't think me asking you how many stereoisomers a molecule has is a particularly interesting question. The answer is either 2, 4, 8, or lots. Because anything above 8 is lots. Yeah, you probably need to know it, but again, you have your notes in front of you for every evaluation. Okay, any other questions? Okay, so good luck with the labs, and I will see you on Wednesday, and the next Mobius assignment is next week, not this week. Take care. Bye.